Hey, good morning, everybody, and thank you for coming to this workshop on confirmatory factor analysis. My name is Matt Madison. I'm a faculty in educational psychology and director of the new Quantitative Methods Consulting Center, or QMC. Before we get started, you can access these slides and materials at my website, matthewmadison.com/workshop. You can download a little zip folder and it has all the materials in there, the slides, the data, and the software we'll use. Today we're actually using Mplus. So if you have it on your laptop, that's great. Otherwise, you'll need to log into the computer lab computer to use Mplus. There's also R syntax in there as well, so you can use that, either one. They both do the same thing. I just want to use Mplus this time. We used R last time, and I want to show Mplus and show some of its capabilities. So I'm going to give a brief intro to the QMC, and then we'll get into the topic of today, confirmatory factor analysis. It's just a few of us in here, so please ask questions. We can have discussions as much as you like. I have a few slides prepared, but we have plenty of time, so no worries. So the purpose of the QMC is to provide quantitative research support, and that can look different depending on where you're at in your research. If you're just starting, we can help you plan. If you've already collected data, we can help you analyze. If you've already analyzed, we can help you interpret or maybe help with your software. So we can help at any stage. And then the other part of our purpose is to provide training. And that's kind of where these workshops come in, is to provide training for different methods that we find important, but also ones that you may find important. So if you have topics that you want to be trained on, feel free to submit a request and we'll prepare a workshop if there's demand for a topic. So our QMC team, we're actually all here today. We got Beltran here, Ashley and Nancy. So we all work together to provide support for the college. So if you are in need of support, please submit a request. All right, so getting into today, so for the fall, our workshop is Basics of Measurement Modeling, and it gives an introduction to structural equation modeling. And we thought it'd be good just because SEM is a widely used method in the social sciences and specifically in educational research, where we're dealing with latent variables, things that we can't see, but we know to exist and we know have an impact on student learning, and all sorts of things inside school. So we thought it was a good method. But again, if you have any other ideas for workshops, let us know. So getting into SEM, it's comprised of two foundational methods. The first is path analysis. So if you look at this diagram here, this is a path diagram of a multiple regression model. So you got some independent variables, some predictive variables. You got growth mindset, content knowledge, pedagogical content knowledge, and you got all of those variables working to predict student achievement, which is an outcome that may be of interest. So this is your traditional multiple regression model. So with path analysis, what we're doing is we're shifting away from this all variables going into one to where we can specify a more nuanced relationship about how we believe phenomena to behave. So we may think that growth mindset impacts content knowledge, and which impacts student achievement for your teachers. And we also may believe that growth mindset impacts pedagogical content knowledge, which then impacts student achievement. And so in this case, we hypothesize that there's no arrow going from growth mindset to student achievement. So this is what we call mediation relationship. And this is what path analysis is for, to allow us to specify these different types of relationships. So this is the first part of structural equation modeling. And this is what our first workshop was about. If you go to our YouTube channel, you can watch that video. And the second part of SEM is confirmatory factor analysis. So one limitation of this path model is that you can only model observed variables. So those are visualized with rectangles, right? So these are observed variables. We assume there's no measurement or no error when we measure them. But we know if we're using instruments, surveys, different observational methods to observe these things, we know there's going to be error and we need to account for it. And that is done with a confirmatory factor analysis, or a CFA. So what we have here is a theory that our latent variable, visualized with a circle or an oval, is driving responses to these items. That is what we hypothesize. So that's a common thing throughout all these things. SEM is that it's always a theory kind of underlying what we're doing. And so what we theorize here is that growth mindset is impacting or is driving responses to these items. All right, so the benefits of CFA are that we are properly modeling our latent variables, accounting for the measurement error. We get to assess our instrument's reliability and our item quality. We can make our instruments more efficient, possibly by dropping redundancies and including really good items, or improving it by adding more items, whatever we need to do. So what happens is when we account for the measurement error, we can reduce bias in our inferences and make more accurate predictions and really learn about what's happening. All right, so we move to the full structural equation model. We just combine a path model with the CFA. All right, so what we get here is we got the same variables we had before. So now each of them has a little mini CFA attached. So growth mindset is a latent variable that we're modeling with some sort of instrument. Content knowledge, pedagogical content knowledge, student achievement, all measured with some sort of instrument. And we're accounting for the measurement error in them. All right, so this is a full structural equation model diagram here. All right, so the benefits of SEM, we get to model these complex relationships. That is done through the path model aspect. We handle the measurement error appropriately. That's done through the little CFAs that represent our latent variables and the ovals. We get improved power and inferential accuracy, so we won't make mistakes. And when we're trying to capture these relationships, trying to figure out what's happening here. And SEM is foundational for many other methods and techniques for growth modeling and different approaches. So we thought it was foundational. So that's where we're starting with our fall workshop. So today is all about the second part, which is confirmatory factor analysis. All right, and again, these slides are available at my website, matthewmadison.com/workshop. So I'll give a conceptual introduction to CFA, talk a little bit about the technical foundation. I won't get too deep into a lot of the equations and technical things, but just enough where we can understand what's happening. And then we'll talk about how you evaluate fit and improve your model. And then we'll do an empirical demonstration in Mplus. So I'll do it in Mplus, but again, there's our syntax in the material, so you can use that if you like. And we'll go through fitting a couple different models and improving the fit based on the model fit metrics and information criteria. And then I'll provide some resources and extras if you want to learn more about CFA. So I'll start kind of with what you would do if you had a survey and you didn't really know about measurement theory. You would simply add everyone's items together, and you would treat, so yeah, let's say you had items measuring external motivation on the Likert scale, 1 through 5. You had 5 items, right? You would just add those items up, and that would be a person's score, and then you would subsequently use that in a regression model. And this is actually the natural thing to do, and there's a whole theory that lays out how to do this. It's called classical test theory, where that overall score is called an observed score. And in classical test theory, CTT, the overall score has 2 parts. It has the true score, which we believe to be driven by the latent variable. And then there's error, which is error in how we're measuring it, right? Which we can't get away from. All right, but the issue here is that our true score, our observed score is unreliable, right? If it were perfectly reliable, we wouldn't need any of this, but we know it's going to be error until it's unreliable. And so reliability in the classical test theory framework, there are different ways to think about it. You can think about it as kind of consistency over multiple measurement occasions. So if we could wipe people's brain clear and have them take our instrument again, would they get the same score, or would it shift a little bit? You can also think about it as proportion of variance in the observed score that's actually due to the true score. So how much of that is actually real variance and how much of that is just random fluctuation and measurement error. All right, and today we're going to talk about why it matters, and it's because it affects our inferences and what we say about our variables. We're trying to capture relationships in our variables, and we're going to make mistakes if we don't account for unreliability. That's what we're trying to account for. All right, so in that path model earlier in the full structural model, the only difference is that the path model includes only observed variables, right? Whereas our SEM includes latent variables. And so our observed variables like height and income do not have measurement error. We can measure those perfectly. But when we have latent variables like growth mindset or external motivation, in an SEM, the paths, the regression coefficients are corrected for measurement error. All right, path analysis can't correct for unreliability, so your estimates are going to be biased. In fact, it is directly proportional to the unreliability of your instrument, how biased those estimates are going to be. And CFA is what helps us account for the measurement error and unreliability in the SEM. All right, I mentioned this earlier, but our CFAs are based on theory, all right? And it gives us a method to test those theories. All right, so you can specify a model based on what you think about what's happening in whatever area you're in. So that means the number of latent factors. So how many factors do you have? How many factors do you think are driving responses on your instrument? And then kind of how those factors load onto the items, right? So that's kind of the factor item loading structure. So this example here is just one kind of from educational psychology. So let's say we're interested in measuring motivation, and we believe that there are two types that we're interested in. We got external, and we got 5 items that measure external. And then we got internal, and we got 5 items that measure internal. And so again, our latent variables have the ovals, and we have an arrow between them indicating that they're correlated. We believe that they're correlated to some degree. And then we got arrows directing to the items, these observed variables, the rectangles. We believe external motivation to be driving responses to these items. And then we got internal motivation driving responses to these items. And in this case, there's no overlap, right? So it's not like internal impacts that item. So this is called simple structure, where each of your factors load onto, or each item only has one factor loading onto it. All right, but this is a theory. Again, we don't know. We're going to let the data kind of inform us about how accurate our theory is with respect to the data we collected. Now, we call it confirmatory factor analysis, but it's not fully confirmatory, right? When you collect your data and you analyze it, the results allow us to adjust our theory, right? That's the great thing about it. So it's not 100% confirmatory, but if you're on the other end and you have no clue what your instrument is measuring and you want the data to tell you what it's measuring, you can use an exploratory factor analysis when you really don't have a good theory or a good hypothesized structure to it. So what happens is, in this case, you run several models and you compare the fit and you let the data tell you how many factors there are and you let it tell you how the factors load onto the items. And then if you want to validate that, you would then follow it up with the CFA on a different sample or a subsample from the sample you collected. But CFA, you have a good theory and you're trying to confirm that theory or validate that theory. All right, so I mentioned simple structure earlier. Each indicator is typically, sometimes, I won't say typically, I say sometimes hypothesized to explain by one latent factor, so we have simple structure. In this previous example, it was simple structure. It doesn't have to be that way. A lot of times it makes your life easier as an analyst and to interpret things if it's simple structure, but it doesn't have to be that way. A lot of times, sometimes as a content expert, you can say, I think this measures this, and you empirically may measure multiple things. And then to simplify, you may have it only measure one. It's like the decision you have to make between what the statistics are telling you and what you know from your field knowledge and expertise. So it's always a balance there. All right, so a little bit of the technical foundation. To identify the model, a couple things need to happen. So this is a latent construct that we're dealing with. And so there is no inherent units to them, right? We don't know whether, it's not like a test you give where it ranges from 0 to 100 and you know that 90 is good or above is an A. These latent constructs, there is no units to them. So we have to give them units. And we do that either by fixing the first loading to 1, which we'll see in Mplus as the default, or you can fix the factor variance to 1. So one of those has to be done in order to identify the model. It's not too important for now, but it does become important later to how you interpret your model. We'll see that. And then there had to be a certain number of indicators or items. So if you're doing a one-factor model, you need at least 3 items to identify the model. And if you have more than one factor, then you need at least 2, preferably more, to avoid empirical under-identification. So statistically, all you need is 2 or 3, but preferably you want to have more so that you get good reliability and validity, and you cover the breadth of your construct. All right, so back to our path, our diagram, our CFA diagram. So we got these 2 latent constructs. They're typically denoted with the Greek letter eta. All right, so we got eta 1 representing our first factor, external motivation, and we got eta 2 representing our second latent factor, internal motivation. And then we got our arrows, our loadings, which represent the strength of the relationship between our factor and our items. Those are denoted by lambda. All right, so for our first factor, it's lambda 1, 1 for the first item, lambda 2, 1 for the second item, and so forth. All right, and then for our second factor, we got lambda 6, 2, this is item 6, but for the second factor, 6, 2, 7, 2, all the way to 10, 2. All right, and then out here, we got our error terms, right? Because what we'll see in a second is that each of these is like a little mini regression model, right? That we think this is driving the response to this, and we can predict this if we know this and we know that. So it's kind of like a little mini regression. But of course, in regression, you have an error term, right? You can't predict it perfectly. There is some error there. And so we have these error terms out here. So now we're capturing that error. All right, so generally, this breaks down to item score. It's going to be an intercept plus the loading, which is kind of the regression slope, times the factor plus some error, right? So what it looks like is you got your first item score is going to be lambda 1, 1 times the factor, the loading times the factor, plus the loading for the second factor times the second factor, plus an error term. But in this case, this does not load onto item 1. So it actually, that loading is just set to be 0. So that one goes away, and we just get lambda 1, 1 times eta 1 plus epsilon plus the error term. All right, and this is what simple structure does. It simplifies our little mini regression down to just a loading and the factor itself, not the other factor coming into play. And in this case with simple structure, this goes all the way down for all the items that simplify like this. All right, and then if you want to interpret these mini regressions, they're just like regressions. So if you're using unstandardized coefficients, then the slope is just a unit change for every in the item or in the item score for every unit change in the factor. All right, but typically we use standardized coefficients in this case because it impacts our interpretation. And what it does is if you have simple structure, then the standardized coefficients are just correlations, which makes it really nice and easy to interpret. All right, so then when we do standardized coefficients and we go back to our diagram, all right, then our loadings are just correlations between our factor and our items, right? So we want those correlations to be big, approaching 1 or -1, indicating a negative relationship, but further away from 0 the better, right? The stronger the item is. All right, so model fit. So this is similar to when we discussed path analysis. There are some metrics we can use to evaluate our model and potentially improve our model. And here we're going to keep it basic with some of these metrics. These are the ones that are provided in R and Mplus and most software. I'm giving the general cutoffs, but there's some debate about these. It changes depending on the context and the complexity of the model and the sample size. But generally, these are ones that are used. Recent work has kind of looked at this in a more dynamic context, but for today, we can just use these basic ones and start there. All right, so we got the chi-square test of model fit. So it's an overall test of model fit. It's a global test, so it doesn't tell us where the misfit may be. It just tells us something's off, right, potentially. So what we're looking for good fit is that we get an insignificant p-value, so something bigger than 0.05 or whatever alpha you're using. This is very sensitive with with large samples. And so most of the time when you have a good sample, I won't say it's useless, but it's not as informative, right? We kind of look past it because most of the time you're going to get a significant chi-square test. So we kind of look past it and we look to some of these other metrics to give us a better idea of what's going on. So one is RMSEA, or root mean square error. We want that to be less than 0.05 or maybe 0.08 for acceptable fit. We got standardized root mean square residual, or SRMR. It's similar to RMSEA, want to be less than 0.05 or 0.08, around there. And then we got CFI and TLI. We want those to be big. So we want those to be greater than 0.9 or 0.95 to indicate good fit. And I mentioned earlier that kind of these things are foundational because these fit statistics are used all throughout kind of introductory all the way through advanced statistics. So it's really good to learn these because it's foundational. The fit stuff stays the same as you work your way up. Improving the model. So how do you improve it? So let's say you get a poorly fitting model. Well, a couple of different things you should look at. One is to look at the factor loadings, right? How strong are your items? All right, you can look at the factor correlations, right? Because you are hypothesizing a structure, right? The correlations and the loadings can give you some indication of how correct or incorrect that hypothesized structure is. All right, another thing you could look at is the standardized residuals. So in this case, we're trying to capture relationships among these variables, right? And so we're trying to capture the correlation matrix essentially. And so these standardized residuals tell us how far our predicted correlation matrix is away from our observed correlation matrix. And so we standardize them, and anything bigger than 2 or 3 are kind of like red flags to indicate where the misfit may be. All right, most softwares will also include what are called modification indices. So these are statistically driven suggestions to improve the model fit. But we have to caution because these indices are theory agnostic. They don't know anything about what you're measuring, how you're measuring it, or anything about substantive knowledge. And if you follow them, rarely do they lead to actually the true underlying model. So you got to be careful. You got to make sure that if you're going to use something from the modification indices, that it actually makes sense to your content experts, or if you're the content expert, makes sense to you. And so really all these statistics provide information that can help you understand the relationship with your variables and lack of fit that may be present. So it's kind of a holistic picture you're trying to paint, and you got to use all the fit to kind of help you build that picture. All right, so that was conceptual introduction. Questions so far? Yes.
I'm sorry I missed the first
Please.
So maybe you covered this, but I know sample size is often a thing to consider, right, when you're doing factor analysis. What is the smallest sample that you would be comfortable doing confirmatory factor analysis on? Like, let's say you had a measure, like a 20 item measure, and you hypothesize a 1-factor structure. How many participants would you recommend?
That's a good question, and I'm glad you mentioned. So I'm repeating for the video. So the question is, what is the kind of general sample size recommendations for CFA? And I was going to say it depends on the complexity of the model. But you mentioned for a 1-factor model, you can get away with a smaller sample size. So Off the top of my head, I would say 100 might be sufficient for a one-factor model. I think research suggests you might be able to go a little bit smaller than that. But yeah, it depends on the strength of those items, right? They're really good items, and you can get away with fewer. If they're weaker, you might need more to kind of capture what's happening there. Those are general numbers. I need to Google and find a paper for you, but those are general numbers. Yeah.
What about a two-factor?
Two-factor is going to be more. I can't quite put a number on it, but it's going to be more. Yeah, the more complex, the more you're going to need. Yeah.
Thank you.
Yeah, the issue is with kind of with the model fit evaluation. So the model fit metrics don't work well with the small samples. They just can't kind of pick up on the nuances that you really want to pick up on. So it gets tricky to evaluate your model in that case. But yeah.
Is there, like, I got a question, like, similar. Is there a way to leverage? So, like, sometimes I know researchers would take instruments that were already applied, and then the theory changes a little bit, and then you probably add some items or modify some, but then you keep, I don't know, 70% of the items. And maybe the original sample is really big and yours is smaller. Is there a way to leverage some information from previous applications of some of the items to kind of help estimate the model with these new items?
That's a really good question. So it depends on what you're doing in that sense, right? If you are trying to validate this theory or test this theory in a different context, if that's your context, well, then you wouldn't want to use any of that information because you want this new kind of setup to be free of any bias from any previous analyses. You want it to be completely fresh, and you want to test it up against theory that already exists. And so in that sense, you'd want to freely estimate it, and you wouldn't want to use any information. If you had a similar sample and you would just wanted to build on it, maybe you could try to fix some of those items, right? From a previous calibration, you could try that. But it depends on what you're doing and the purpose of the study. Yeah.
And if you just can't get that many people, do you recommend using classical test theory or something else?
Yeah, if you can't get a big enough sample to reliably calibrate a CFA model, what's the suggestion? Yeah, then you're kind of forced into the classical test theory, and you just have to note it as a limitation, right? Yeah, but you can always try. And then I don't do a lot of the non-parametric work, but apparently there's some recent work on non-parametric models and different Bayesian methods that may be able to work better with smaller samples. But I'm not as familiar offhand with those, but those are potential solutions for that. All right, so let's get into our empirical example. This data comes from a study called Native STEM Portraits. It's a National Science Foundation grant. It was a mixed method longitudinal study of Native individuals in STEM majors and careers. And part of the quantitative portion of the mixed methods, we designed a survey to measure some important constructs. And they had a hypothesized structure to it. So this was a good situation to use a CFA model to examine the instrument. All right, so first thing I'm gonna do, so this is in the materials, which are available at matthewmadison.com/workshop. So if you go there, you can find the materials. I'll just go to my website here. If you go to my website and then go /workshop, you'll find a zip folder there that you can download. So in that folder, I got a couple of things in there. First thing I'm going to do is I'm going to pull up. Oh no, I forgot to put it in there. I think I forgot to put it in there. I don't think it's not super important, but I'm going to look at the hypothesized structure to this instrument before we look at the data. Okay, so the research team had written some items, and they had a hypothesized structure. So they had I think there were 4 different factors. There was native values, and you can kind of see the items that measured that. There was giving back / nation building. This idea that Native individuals want to give back to their community, their local tribe, Native and indigenous people in general. And then they had institutional supports of indigenous ways of knowing. So that was another factor they hypothesized to be there. Native community involvement, actually 5 factors. Native community involvement, which is kind of how the Native community was involved on campus. And then Native STEM identity, which is kind of their personal connectivity to Natives in STEM. And so they hypothesized a 5-factor structure. And so we started with that when we went into our CFA. All right, and these are all Likert items on a 5-point scale. So I'm going to pull up, I'm going to go into the folder, and I'm going to pull up this file, NSP factor analysis. All right, and I'll kind of walk through this Mplus file. So again, if you want to use R, you can. It's the same analysis in R. I got the R script there if you're interested in that. Come on. So if you prefer R, it's the same analysis in R there. I'm going to use Mplus today. All right, so in Mplus, comments, use an exclamation point to comment things. So just put some comments up here. I got a title for this analysis. I got the data file, how to read it in. So it's nsp.text, and that is here. So we got a bunch of Likert scale items. All right. And then you have to tell Mplus what's in your data file. So use that with this variable section of the code. So I tell it the names of all the variables. So for each column, I tell it I got item 1 through item 27. And I got a use variable line that tells Mplus I want to use all the items. Sometimes you want to take some out. And then if you had any missing data, this one doesn't have any. But if you had any, you put your missing data code here. And tell Mplus what your missing data code is. So we do that. Then we get into the measurement model, the CFA model. And this is relatively straightforward. You just take your construct. So in this case, we had 5 hypothesized, right? All here. We had native values, giving back, nation building. All right, so I got native values, and I got a hypothesized measure item 1, 2, 5, and 9. That's exactly what we got here, 1, 2, 5, and 9. And I just go one by one on all my factors, hypothesized factors, and I have them loading onto the little by statement, tells it how it loads, and I got loading onto those respective items. So that tells Mplus the loading structure. All right, and then I'm going to ask Mplus for some output, some statistics. So I'm asking it for sample statistics, I asked it for standardized solution, modification indices, and the residuals. And then if you want to, we're not doing it in this example, but if you want to, you can output certain things into another file. So the factor scores, I can output them into another file if I wanted to use them later in a different analysis. And that's done with the save data command here. All right, but let's run this and see what Mplus tells us about our hypothesized structure. So I hit this little red button here, run. All right, and it ran. So first the Mplus does an output file. It kind of repeats what I input. All right. Input reading terminated normally. So that's the first check that Mplus did what you wanted it to. Then it gives me some general statistics, or not statistics, but summary of analysis. So number of groups, number of observations, number of dependent variable, those are the items, number of continuous latent variable, those are my factors. So it tells me what's happening there. Gives me my items and my factors. A little bit about the estimation. We didn't have any missing data, so all that's there. Some sample statistics, some item correlations or covariances. They gave me some sample statistics for the item. So item 1 had a mean of 2.4, variance of 1.275. So give me all those for the items. All right, and then, so this is not the best thing when you see this. So estimation terminated normally, that's great, but it does give us a warning. And Mplus gives a lot of warnings, but sometimes it's worthwhile to take a look and see what's going on. So you can see it's telling us that a correlation greater or equal to 1 between 2 latent variables or a linear dependency among more than 2 variables. So check the output for more information. Problem involving variable NCI. So that is, what was NCI? Native community involvement. So it's telling us that something is up with that variable. So we giving us indication that something's going on, but we can take a look and see. All right, so then we get into the model fit. So first thing, gives us our chi-square test of model fit. So that is here. And you can see it is significant. So, but with the sample size of 400, it's probably going to be significant. So we want to look at other statistics to try to tell us what's happening. All right, look at our RMSEA. It's actually pretty solid. 0.06 is below 0.08, kind of in the good range. CFI and TLI, those are pretty good too. So this is looking good kind of initially, right? It looks pretty solid. SRMR 0.067, so that's pretty good too. So this is rare when you get a data set to fit this good. I couldn't find one that didn't fit as well, but we'll see how to improve it. So now I'm going to go to the standardized loading, because that's the first thing you want to look at, standardized loadings and the factor correlations. So I'm going to keep going, and I get down to STDYX standardization. So this is where it tells us the loadings for our model. All right, so first thing I'm looking at is the loadings and their significance. So I had native values on items 1, 2, 5, and 9. Look at the estimates and their p-values. So these are correlations. So I want them to be big. And I'm looking at item 1 and 2, and these are pretty weak, right? We've got about 0.05 correlation, 0.03, and they're not significant. So perhaps there's something going on there. Those items are pretty weak. All the giving back items look pretty solid. Institutional support, those look solid. All those look good. We got another pretty weak one here with item 27. All right, but also we look at the factor correlations. So let's take a look at that, because the Mplus told us there might be something going on there. So giving back with native values, 0.967. All right, so that's a pretty big one, right? That is close to 1, which is either an indicator that they're the same thing, that you think you're measuring something different, but it's actually just one thing, or that you weren't able to capture the distinction between the two with your items, right? So either one, we need to think about what to do with that. And then we got a really high correlation here between community involvement and institutional support. It's actually bigger than 1. So that's what Mplus was flagging us for, that you actually got a correlation bigger than 1, which happens when you have a dependency and Mplus gets kind of confused and estimation. It messes up when you have a dependency like that. So what I'm seeing here, if I'm an analyst, I'm thinking, okay, we got some weak items, but we also got some really high correlations. At this point, based on what I'm seeing here, I probably would combine giving back and native values into one construct, because those are so highly correlated with each other. And I'm also going to combine, or actually not yet, I'm going to think about it, right? As an analyst, I'm thinking about these things. What I would do is I'll take it to the content expert and say, hey, what do you think about this? So when I took it to him, we took a look at the items. So giving back and native values, I told him that these items were all super correlated. And we looked at the items together. And if you look at the items, if you just like just look at them kind of substantively, they are all kind of measuring some, I don't know what you call it, but it's some native values, like these are all very similar to each other. All right, so it makes sense that they're correlated. And so then it made sense to combine those two to the content experts. So that was one change we made. And then if we look at Native community involvement, which was hypothesized to be highly correlated with institutional supports. So if we look at these items, the gray items, and we look at the blue items, so other Native students feel welcome to valued institutions. My institution has the coursework, activity, and programming needed to attract large numbers of Native students. My Native community knowledge and experience are recognized and valued at my institution. So this was another case where, though we thought we were measuring something different, empirically we weren't, and the items, they were very similar to each other. So that was another change that we made. So those were two immediate changes that we made. All right, so I'm going to go back into Mplus. I'm going to go to my input file. Let me go back to my input file. Wait, can I look at the diagram? Not yet. Okay. I'm going to reduce this to a 3-factor model. I'm going to combine native values and giving back. All right, so I'm going to take these items. All right, I'm going to put them up here. There. And I'm going to call it native. I'm just going to combine those two. I'll get rid of that one. All right, and then NCI and institutional support, I'm just going to get rid of NCI and I'm going to put item 13 to 15 up here. All right, and I'm going to get rid of Native community involvement, and that was already inside institutional support. All right, so I'm changing my factor structure based on the output and what our content expert told us. All right, so now we got 3-factor model: native values / giving back, institutional support, and native STEM identity. Right, so now we got a 3-factor model. And I'm going to save this as model 2. So I'm going to save that model 2. Okay, cool. All right, I haven't done anything to the items yet because I want to see what happens now that I've changed the factor structures. Potential that the item logins could change now that I've changed things. So I want to see what happens now. All right, so let's run this one. All right, let's see what we got. All right, so I'm hoping that little warning doesn't come up because we got rid of that dependency. So let's see. That's covariances. Keep going, come on. Okay, so we terminated normally and we did not get that warning. So that's a good sign. All right, our model fit, we still failed the chi-squared test. And our fit still looks good. Our MSEA is big, or excuse me, small. Less than 0.08. CFI and TLI are bigger than 0.9. That's a good sign. Our SRMR is less than 0.08, so that's good. All right, so we're looking good so far. Now let's go down to the standardized. Okay, so now we got native values given back, and we got all these items. Item 1 and 2, so even with the combining into one construct, these are still weak items that aren't contributing much and not significant. So those are 2 items we want to look at. Institutional support, these look pretty solid, ranging from 0.6 to 0.8. That's pretty good. And then we got native STEM identity. These look pretty solid as well. Item 27 is the one weak one. Not looking too good. Also, I forgot to look at the diagram. This is why I like Mplus. You can, the diagramming is really nice. So we got a 3-factor model. Let's see if I can zoom out some. My computer's too small, but all the loadings are here. And if so it's showing the unstandardized ones. If I do, what is it? View STDYX estimates, standardized estimates, then it'll give me the standardized ones. All right, so these are my standardized loadings. And it's also giving me, once you standardize, then these out here are correlations. So I got a big correlation between native values and native stem identity, 0.786, so that's pretty large. And then we got smaller correlations between the other three. So that's what we got going on there. But we still got a couple of weak items that I think are not needed. So I'm gonna look at item 1 and 2 with the weak items, with the weak loadings. I'm gonna look at item 27. So I went to the team and I said, okay, these items are not really loading well. So native values here, these two were not really good items, right? And then item 27 was also not, this item was not loading well on native stem identity. All right, so because they weren't loading, and the team didn't really feel strongly about them, we just dropped them. I'm kind of going out of order here of our real analysis, but what we did was we estimated reliability first, which we'll get to in a second. Estimate reliability and make sure that if you drop an item, it still remains above whatever you need it to be. You don't want to drop items and then your instrument become unreliable. Okay, so that's just the diagram. Next thing we did was drop those items. So I'm going to drop items 1 and 2. So I'm going to get rid of items 1 and 2. So now I'm going to use variables item 3 through 26. I'm dropping item 1 and 2 from native values. So those are gone. And then I'm getting rid of 27 as well. That one's pretty weak too. So there we go. All right, let's run this and see what happens. Because we're trying to achieve a parsimonious model that that captures the structure, but also is not having any redundancy or waste. So we're still good at terminated normally estimation. Oh, our MSA got a little bit worse, but that's okay. It's still solid, 0.081. SRMR went up a little bit. That's okay, still below 0.08, so we're still okay. Let's check our loadings and see what we got. All right, so now we got all significant loadings. They look pretty good. All right, for our 3 factors. We can see our correlations here, 0.3, 0.3, and 0.8. So we're good there. Where's my... All right, so right now we're looking good, right? We got a decent fitting model, right? It matches what our content experts thought. All our loadings are significant, and it matches kind of what our experts thought. So now we're looking at, well, how can we improve this, right? So everything looks pretty good, but how can we improve it? So what we can do is we can look at, if we go down, I mentioned, oh, here's another thing we should discuss, which is, remember I mentioned that each item, or each arrow is kind of like a little mini regression. So for each item, you get an R squared, right? Proportion to variance explained. So you want these to be high. These are related to the correlations, to the loadings. But you want these to be high. All right, and then we can look at the residual output. So it gives a lot of residuals, but the ones we're interested in are the standardized residuals for the correlation, or for the covariance or the correlation. So let's see if we can find it. Here we go. All right, and there's a lot. We got 27 items here, so there's quite a bit going on. And it's actually going to be kind of difficult to look through. But what we're looking for is values that are bigger than outside of 2 or outside of 3. So anything that's really big, we want to take a look at. So you see we got one for item 5. There's one. So what you want to look for is ones that kind of collect on certain items. So if you have an item that has a lot of big numbers going across or down, that's an indication that perhaps something is going on. Let's see, I'm looking for big numbers here. I do see some that are bigger than 3, but not consistent. Like this one, item 14, I got a -4 here, -3. So that one may be worth looking at. I see item 22 here. I got an 8, a 7, a 7, a 6, an 8. So this one is pretty pretty big residuals, so that may be worth one looking at. Let's see. Yeah, so you just want to take a look at all of them and see if you see any patterns in there. But for time purposes, I'm going to go down to the modification indices, and I'm going to check out what it says. So I mentioned that modification indices are statistical recommendations, statistically driven recommendations, that basically this number here, or these numbers, they tell us if you were to make this adjustment. So if I were to add item 12 to this construct, to native values, it would reduce my chi-square statistic by 15.8, right? So telling me how much improvement is going to be achieved by making this modification. So generally what you look for are kind of large values. Sometimes people say 10 or more, you want to take a look at it. But once you get multiple that are 10 or more, you want to look at the biggest ones to try to make the most bang for your buck, right? So in this case, we got one here. Native values by item 22 is at 238. So this is one where we could potentially improve our model quite a bit by having native values load onto item 22. All right, so I took it to the team. We took a look at it. All right, let's go back to our items. Let's look at item 22. We had it on native stem identity. Here it is here. And it is important for me to persist because native voices are needed in my field. So we thought that might be native stem identity. But empirically it's looking like it is more related to native values, which makes sense in the context of the item and the constructs themselves. And so the team agreed that we could, it was justified to move that to the other construct. And I'm doing this quickly, but what you would do is you could either put it on both, you can move it to the other, you can compare the fit and see kind of how it works. I'm going to do this quickly. I'm just going to move it over to native values. So I'm going to take item 22 from down here. So I'm going to go item 21, then item 23 through 26. And I'm going to move item 22 up here. All right, so now item 22 is there. Let me close this. No, not yet. Okay, let's save it. Let's run it. All right, so now let's take a look. Let's make sure everything is working. All right, so we're still good. Terminate normally. Our fit got better. All right, we're down to 0.06. We still failed chi-square. That's okay. But we're good on RMSEA. We're below 0.08. We're good on CFI TLI. SRMR is looking good, below 0.08. Let's go to our standardized results. We got good. So item 22, yeah, it's pretty strong here. It's pretty strong here. And our model fit improved and made theoretical sense. So that was actually a good modification to listen to. All right, our correlations are still there. Let's see, if we go down to modification indices, let's see, here we go. All right, so again, it's going to keep giving you stuff, right? And we took a look at a lot of them, right? It's saying, institutional support by item 8. Let's take a look at item 8 and see. All right, item 8 is here. Does that measure institutional support? It's important. Well, that's not it. Here we go. This one. I chose my major because I want to help others. Does that measure institutional support? Doesn't look like it, right? So statistically, it's picking up something, but it wouldn't make sense to switch that. So we didn't. And we did that for all these different ones. And there was nothing that made theoretical sense to switch. And so we kept our model. It fit well. It matched with what our content experts thought. So this is an example of kind of modifying a model, modifying things based on both theoretical input and statistical input. Questions on that empirical example? Questions or comments or thoughts?
best example. I like the way you took us through that.
Great. Great.
So when you go to write it up, do you essentially just walk the reader through, like, we started with this, and then these 3 items were looking kind of weird, so we got, I forget exactly what we did, but
Yeah.
do you just go through each of those, or do you, how do you present it?
That's a really good question. So, yeah, you want to be as transparent and open as possible about your analysis. So, in your write up, you'll essentially walk through what you did. So, we started with this theory. This is what the data told us. This is what, this is what the item looked like. And so we decided to move this. And yeah, you'll just walk through your analysis and be straightforward. Yeah. Yeah. There's nothing wrong with being wrong, or you're not necessarily wrong. It's just making adjustments to a theory, and being straightforward about that. Absolutely. Yeah. Really good question.
What were the correlations at the end between the factors?
Yeah, let's take a look. So, if we go to our standardized, we can look at the diagram or the standardized output here. I'm going to go to standardized output since I'm already here. So we ended with 0.7 for native stem identity and native values, 0.75, and about 0.3 for the other two.
Does that look fine to you? 0.74?
It's strong. It's a strong correlation. It's a strong correlation. I wouldn't say it is strong, but not too much to question the dimensionality of it. So when you get to 0.9 and above, that's where you start to question dimensionality and whether you actually have multiple things happening there. Yeah.
I guess Mplus is expensive.
It is expensive. It's like 800 for like the base package or something like that.
But it's in this lab.
It is in this lab. Yeah.
And this lab is available? When? How?
I'm not sure what the hours are, but whenever I'm here, it's always open.
Yeah, you can see in the doors, you can see there's like an e-ink display, and it shows the classes and the times.
Okay.
So if
And
they're
the
not,
times.
if there are any classes, you can. And there's only like 2 a day at most.
Yeah.
So yeah.
It's pretty open.
What is your preference?
It depends on what I'm doing. Like my training, I did all this in Mplus, and so I just feel more comfortable with it. It's just I can do it quickly. But like us, like we have people working in the consulting center who use R for everything, right? So it just depends.
And that's a team.
Is it art free?
R is
Yes.
free, yes.
But but the problem with R is you need to be careful with the packages you install. Not in terms of like security as much as you need to really trust them methodologically. But Laban, it's really
legit.
mature. So yeah. So the packages that deal with this kind of topics, they're pretty good.
And R is installed here as well.
It is, yeah. And R is free, yeah. So that's why we always include R in case, because we know researchers love R for exactly that reason. It's free, it's open source. Yeah, so we got the R syntax in there as well if you want to play around with that. Yeah. So just to wrap up here, just some CFA resources if you want to learn more. There's a measurement theory text by Debbie Bandelos, one of our former faculty. Great text. YouTube is, of course, a great resource. You got CenterStat, QuantFish, our QMC YouTube channel, and many more. If you just go on YouTube and search CFA Introduction, you'll find a lot of good stuff and a lot of different software demonstrations. We have several courses that get into CFA in a lot more detail than we did today. There's a lot more things you can do with it. A couple here. One thing that's often done is measurement variance testing. So if you had different subgroups in your data, like in this data, we had professionals and students. And so we had to test for measurement variance across those. So you want to see whether your instrument functions similarly across these different groups. And it's kind of a requirement if you're going to be using it in different populations that you have this. And it's also a good research question. If items are functioning differently, then why might that be the case, right? What's happening there? So it's an interesting thing to examine, and it's a fun thing to look at. And if you do establish measurement variance testing, you can do latent mean testing. It's like once we established measurement variance, we were able to test kind of who exhibited more native values, right? Was it the students or the professionals? So interesting things can come out of your CFA beyond kind of validating your instrument, or questions you can answer and questions that come up. But if you have more questions, of course, visit us in the consulting center. You can submit a request on our website or email us. And yeah, I'll end it there. I'm over time, but thank y'all for coming.